Welcome to the fuel system lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: an overview of the fuel system and its configuration, fuel parameter indicators, fuel types used in the system, fuel pumps and their power sources, fuel valves and their power sources, integrated safety measures and redundancy, and a lesson summary. So, what is a fuel system, and what are the nuances and specifications of the 737NG's fuel system? Its maximum capacity is quoted by Boeing as 46,063 pounds, but the aircraft can in fact carry 470 pounds more than this. You'll learn how shortly. As well as its obvious purpose of containing and distributing fuel through, the system also has the auxiliary purpose of cooling hydraulic fluid. Each main fuel tank contains a heat exchanger, and both units are identical. Although this arrangement is very effective for cooling hydraulic fluid, the fluid does not carry the sufficient thermal energy to heat the fuel in any significant manner. So it's important to emphasize that the fuel system does not heat the fuel. Conversely, the engine fuel feed system, discussed in the engines lesson, features heat exchangers to cool oil from the integrated drive generators. These, however, intentionally heat fuel. Fuel is typically stored in either 2 or 3 tanks. However, contrary to popular belief, the 737NG is actually fitted with 5 tanks. Each tank is integral to the airframe, thus is made of exactly the same aluminum alloys as parts of the aircraft surrounding it. Each fuel tank is made up of alloys of aluminum, zinc, copper, and magnesium in different proportions. The 5 fuel tanks in the 737NG are main tank 1, center tank, main tank 2, left surge tank, and right surge tank. Main tanks 1 and 2 are located in the wing boxes, with main tank 1 on the left and main tank 2 on the right, also corresponding to the way both engines are numbered. They each contain up to 8,630 pounds of fuel. The center tank is located largely on the fuselage but does extend into the wing root, and it carries 28,803 pounds of fuel, but is only filled after the 2 main tanks, and when filled, it must be consumed first in flight. The primary reason for this is to reduce airframe stress. Fuel in the main tanks provides ballast for the wings, holding them in position when the great stress of the aircraft's mass is placed upon them shortly after takeoff, preventing a large change to the wing dihedral angle. This effect is so great on the Boeing 747 that if only the fuselage tanks were to be filled, leaving the wing tanks empty for a high gross weight takeoff, they would simply snap. The 2 surge tanks are located directly outboard of the main tanks, containing up to 235 pounds of fuel each. They are not counted towards the total fuel capacity of the aircraft, but instead provide a precaution in case any form of tank overfilling was to occur. As well as the fuel tanks themselves, the 737NG fuel system has 3 other primary elements: fuel pumps, fuel valves, and fuel quantity indicators. The pilot uses the following panels in the flight deck: the fuel system panel on the overhead panel, the overheat fire protection panel, and the control stand, specifically the engine start levers. Each will be discussed in significant detail as we move along in this lesson. Let's talk a bit about the fuel quantity indicating system. This section of the lesson is about all aspects of the aircraft's fuel system, which display and monitor its parameters based on the FQIS, or Fuel Quantity Indicating System, as well as the Fuel Temperature Indicating System. The FQIS measures the mass of fuel in each tank in either pounds or kilograms and relays the information to the Common Display System, which processes the information and sends it to the flight deck display units, or DUs. As well as the DUs, this fuel mass information is also sent to the fueling panel, located on the right wing, several feet outboard of the number 2 engine. The fueling panel will not be covered in this lesson because it has no incidence in the PMDG 737NG. The Flight Management Computer, or FMC, also receives this fuel information, not from the FQIS, but instead directly from the data source via the Fuel Quantity Processor Unit, or FQPU. The FQPU is always connected to 2 DC power sources. However, only one needs to be powered for the system to be active. Despite being powered from up to 2 sources, though, it can draw current from 3. The 28-volt DC battery bus, the 28-volt DC hot battery bus, and the 28-volt DC bus number 1. Because it can draw from the hot battery bus as well as the battery bus, the battery switch does not need to be on for it to receive power. DC bus number 1 will only power the system if the fueling panel door is closed, and because the bus itself receives power from a transformer rectifier, usually TR1, one of the AC transfer buses must be powered. The battery bus is the regular source of power provided the battery switch is on. As well as calculating fuel mass for each tank and relaying it to the Common Display System, FMC, and fueling panel, the FQPU monitors the system for faults, which are then stored and made available on the maintenance pages of the Control Display Unit, or CDU. The FQPU calculates a mass figure for each tank by using either 2 or 3 devices: fuel units, compensators, and it purchased as a customer option, a densitometer. The fuel units measure fuel weight. The compensators correct for differences in fuel properties, and the densitometers, as the name suggests, measure density. The reason that the densitometers are a customer option is because the fuel system is still very accurate without them. However, when fitted, fuel quantity indicating system accuracy is within 1%. The Common Display System, or CDS, has the fuel information which is needed by flight crew most often. For example, what is displayed on the upper DU. CDS is likely an unfamiliar term, but a good one to get to grips with, as it is to the DUs and DEUs as what FMS is to the FMCs and MCDUs. The CDS is capable of displaying several configuration errors should the fuel system be running abnormally. A low warning will be displayed on either main tank's gauge when its quantity depletes to either 1,000 or 2,000 pounds as selected by the customer. The tank must, however, meet this condition for 30 seconds before the warning is triggered. The warning will disappear when tank contents rise to 2,500 pounds if the 2,000-pound trigger criterion has been chosen, or 1,250 pounds if the 1,000-pound condition is set up. An imbalance warning will display to indicate an imbalance between the main tanks. The quantity difference required to trigger this is 1,000 pounds. This difference must remain for 60 seconds before the warning is triggered. To get rid of the warning, the differential quantity must reduce to 200 pounds or less. This message will only be displayed when airborne. The final configuration message which can be displayed is the config warning, which refers to the center tank. This will display when all of the following conditions are met. There is more than 1,600 pounds of fuel in the center tank. Both boost pumps display low pressure warnings, and 1 or more engines are running. The config warning will disappear when one of these conditions exists. Center tank quantity is 800 pounds or less, both engines are shut down, or one or both boost pumps provides regular pressure. The fuel temperature indicating system is another important indicator of fuel parameters. It's powered by 28-volt AC transfer bus number 2, which is in turn powered by the 115-volt AC transfer bus number 2. So the latter must be powered for it to be functional. When depowered, the needle will go off the scale on the negative side, thus will rotate fully anti-clockwise. The fuel temperature probe is located in main tank 1, as it theoretically contained the coldest fuel. And yes, contained was meant to be in the past tense. This is for a reason which dates back to the 737NG's great-grandfather, the 737-100-200 variants, which had a slightly larger heat exchanger for hydraulic system B than system A. The system B heat exchanger was and is located in main tank number 2, which thus had slightly warmer fuel. There was no reason to change its position, and so Boeing did not. You may have noticed that there are no limitation indications on the fuel temperature gauge. This is because different types of fuel have different freezing points. This is a short but very important section and will teach you a fundamental but simple rule for knowing the limitations of your fuel. In civil aviation, only 3 forms of jet fuel are used, each made to standard specifications around the world. These are the following: Jet A, Jet A1, and Jet B. Jet A and A1 are far more common types, and they consist of longer chain hydrocarbons than Jet B, between 8 and 16 carbon atoms long. Jet B, on the other hand, is comprised of chains between 5 and 15 carbon atoms. Jet A and A1 are known as kerosene-type fuels, whereas Jet B is a wide-cut naphtha-type fuel. Wide-cut fuels are not permitted for use in the 737NG, with potential results being defined by Boeing as engine flameouts and significant power loss. Jet A fuel is used almost exclusively in the United States and is also used in Gander Airport, Canada. Jet A1 is used throughout the rest of the world. Here's a comparison between the two fuels. The freezing point of Jet A1 is negative 47 degrees Celsius. Jet A freezes at negative 40 degrees Celsius. The flash points are 42 degrees Celsius for Jet A1 and 51 degrees Celsius for Jet A. Per pound of fuel, Jet A1 carries more energy. However, as it's slightly less dense by volume, Jet A carries more energy. Jet A is therefore slightly safer to handle on the ground due to its higher flash point. But for cold weather operations, Jet A1 has the edge, of course. The differences are negligible and neither is really superior to the other. The 737NG allows fuel temperature to fall to the higher of the following figures: negative 43 degrees Celsius, or 3 degrees Celsius above the fuel's freezing point. To summarize, when carrying Jet A1 fuel, you must descend to a lower, thus warmer altitude when fuel temperature reaches negative 43 degrees Celsius at the latest. However, as a precaution, you should preempt this and descend earlier. The same applies to Jet A. However, here, the magic number is negative 37 degrees Celsius. Here's the vital rule we promised earlier. You must follow this when calculating your minimum fuel-safe temperature in the approved manner. You take the highest freezing temperature of the fuel used on the last 3 flights. Thus, if having used Jet A followed by Jet A1 twice, a freezing temperature of negative 40 degrees Celsius is to be assumed. In this condition, therefore, the minimum safe temperature in our 737NG is assumed to be negative 37 degrees Celsius. These conditions may seem prohibitive. However, a good pilot should prioritize safety above all else. The 737NG is fitted with 6 primary AC electrical fuel pumps plus, as a customer option, a DC-powered fuel pump to supply the APU with positive fuel pressure for startup when AC transfer buses are not available. This DC fuel pump and its utility is covered in more detail in the APU lesson. The primary fuel pumps are categorized as follows: Main Tank 1 forward pump, Main Tank 1 aft pump, center tank left pump, center tank right pump, main tank 2 forward pump, and main tank 2 aft pump. It should be said at this point that there are another 4 electrical fuel pumps in the 737NG. However, these are part of the engine fuel feed system and are covered in the engines lesson. Each electrical pump is powered by 3-stage 115-volt AC power. They are intelligently placed behind a check valve to allow removal for maintenance without necessitating to defuel the respective tank, which saves time and money should they develop a fault. Other check valves surrounding the pumps are a vapor discharge check valve to prevent fuel from the feed manifold flowing back through the pump. A vapor discharge check valve prevents reverse flow from the tank through the pump. Fuel pump control is located exclusively on the fuel system panel, located on the overhead panel. 6 switches, 1 per pump, on this panel turn the fuel pumps on and off. When the switch is placed in the on position, a relay is energized, which in turn powers the pump motor. Provided the pump is primed with fuel and operational, and its corresponding AC transfer bus is powered, it can be turned on. These pumps are all powered by the 115-volt AC transfer buses. AC transfer bus number 1 powers the center tank left pump, main tank number 1 forward pump, main tank number 2 aft pump, whilst AC transfer bus number 2 powers the center tank right pump, main tank number 1 aft pump, and main tank number 2 forward pump. The 2 center tank pumps are located on the rear spar and accessed through the wheel well. The center tanks will supply fuel at a rate of 20,000 pph to the fuel manifold at a minimum pressure of 23 psi. This is intentionally 13 psi higher than the main tank pump pressure to ensure fuel is consumed from the center tank first. Should pressure fall to 22 psi or less, the low pressure light corresponding to the center tank fuel pump, which meets this criterion, will illuminate, triggered by a pressure sensor located above the pump housing and adjacent to the discharge check valve. After 10 seconds of low pressure, the master caution light will illuminate, as well as the fuel annunciator on the captain's side. Since our aircraft is representative of one built after May 2004, should this occur for more than 15 seconds, the relay, and hence the pump, will be de-energized as a safety measure. This will be covered in more depth in the safety features section of this lesson. Should the pump be shut off automatically, however, the low pressure light shall remain illuminated until the pilot-operated switch is set to off. If, on the other hand, the center tank's pumps are set to off, neither a low pressure light on the overhead nor a master caution shall be triggered. Boost pumps in the main tanks are all interchangeable and supply the engine feed manifold from the main tanks. The forward boost pumps are located on the front spar and the aft boost pumps on the rear spar. Forward pumps are accessed through the leading edge Kruger flaps and aft pumps through the wheel well. They supply fuel at the same rate as the center tank pumps, 20,000 pph, but at a lower pressure of 10 psi. Like the center tank pumps, they're fitted with a pressure switch in an equivalent location, which will trigger a low pressure warning at 6 psi or less. The low pressure light will also be illuminated should the fuel pump switch be placed in the off position. If both forward and aft pumps for a main tank are to become defective and display low pressure warnings, a master caution fuel alert will be triggered. This is the only main tank low pressure scenario that will trigger the master caution. So if, for example, both main tank forward pumps were to fail, but the aft pumps remained operational, the master caution light would remain extinguished. A pump not previously mentioned is the center tank fuel scavenge pump. The center tank fuel scavenge pump is a solid-state jet pump which uses pressure from main tank number 1's forward pump as mode of flow. A jet pump works using the Venturi effect, inducing suction by increasing pressure in a fluid with a converging, then diverging tunnel. A float valve seals this jet pump until main tank number 1's fuel quantity depletes to 4,487 pounds, although this can vary slightly with aircraft attitude, at which point it transfers fuel at a minimum rate of 220 pph. This, however, can be as high as 450 pph. Operation of this jet pump requires main tank number 1's forward fuel pump to be operating, but there's no way in which the pilot can interact with its operation. Like the main tank number 1 forward pump, the jet pump is mounted on the left front spar. Along with the pumps, the fuel valves comprise the engine fuel feed system. The system incorporates 5 valves: the engine fuel spar valves, engine fuel shutoff valves, and the cross-feed valve. A third type of valve, of which there are 2, is also present, the bypass valve. This, however, is part of the engine fuel feed system and so will only be touched upon in said lesson. It should be said that both the operation and application of this valve is limited. It's automatic and used in abnormal situations only. However, since its one cockpit indicator is located on the fuel panel, we didn't want to leave you wondering. The cross-feed valve is a device which allows fuel flow between the left and right engine fuel feed manifolds. Comprising of a body, shaft, and actuator, it's located on the right wing rear spar. The actuator is identical to and thus interchangeable with the actuator of the engine fuel spar valve. Powered by 28-volt DC power from the battery bus, the main difference between the actuator for the crossfeed valve and engine spar valve is that it's powered by the hot battery bus. The valve is controlled by the crossfeed valve knob located on the fuel system panel. When the switch is rotated either open or closed, 28-volt DC power travels through a switch assembly to the actuator. The valve is then moved to the appropriate position. When opening the valve open light located above the knob temporarily illuminates bright as the valve transitions, indicating a switch position disagree. When opening of the valve completes, the light will dim, indicating that the valve is fully open. Upon moving the knob from open to closed, the reverse occurs. The light goes from dim to bright as the temporary position disagree situation is present. When the valve is returned to the closed position, the light extinguishes completely. To cross-feed fuel, the cross-feed valve is opened, and the fuel pumps for the main tank which contains inadequate fuel are to be switched off. It should be reiterated here that fuel is transferred to the engine feed manifold, not the tank. Thus, fuel quantity will never increase in the low-content tank. Instead, the high-quantity tank's fuel will be consumed at double the standard rate, as it's now feeding 2 engines. When the fuel quantities have been rebalanced, switch on the pumps for the tank which had the low quantity before closing the crossfeed valve. It is of paramount importance that both sides of the engine fuel feed manifold stay pressurized at all times, as it would compromise safety by increasing the chance of an engine surge. If an imbalance between main tanks requires rectification before the center tank has been consumed, the center tank pumps must be switched off before transfer is attempted. If this is not done, nothing will happen because the higher pressure center tank pumps will be supplying both sides of the engine fuel feed manifold. The engine fuel spar valves and engine fuel shutoff valves will be discussed simultaneously as their operation is controlled by the same levers and handles. Also, the two move in unison. When operating under normal circumstances, the engine start levers on the control stand are used to actuate the valves. However, under abnormal conditions, the engine fire handles on the overheat fire protection panels can be used to close the valves. The engine fuel spar valves are actuated by a 28-volt DC actuator, identical to that of the fuel crossfeed valve, powered by the hot battery bus. They are located outboard of the engine strut, on the front wing spar of their respective wing. When the engine start lever is positioned from cutoff to idle, the spar valve closed light on the overhead panel will first illuminate bright from dim as the temporary lever and valve position disagree is present. When the valve is fully open, the light will extinguish. When closing the valve, the reverse will occur, with the light illuminating brightly, then going dim. This light pattern will be mirrored by the engine valve closed light when the same action is performed, as the left start lever, for example, commands both the left engine fuel spar valve and the left engine fuel shutoff valve. The engine fuel shutoff valve, or EFSOV, is a solenoid-controlled, fuel-operated valve which is powered by a 28-volt DC current from the battery bus. It is located so that it is the final thing which fuel passes through before combustion, after the second engine fuel pump, a system covered in more depth in the engine lesson. As an important safety measure in the event of a large-scale electrical system failure, a battery is installed to provide power to actuate the fuel shutoff valve and APU fuel shutoff valve, should the battery bus become unavailable. It monitors the hot battery bus's power output, and should it dip below 22 volts, the battery will provide 28-volt DC power to actuate the valves. As well as the engine fuel valves, the circuitry is also wired to the engine fuel spar valves. The bypass valves are automatic valves which allow fuel to be diverted around the fuel filters. The fuel filters are present to remove contaminants and by doing so, prolong engine life. However, if the aircraft has been loaded with a particularly bad batch of fuel, or the filters are nearing needing to be replaced, they may have become clogged with contaminants. To ensure, however, that the engines are never starved of fuel, a bypass mechanism is installed around the filters. Should this bypass have to be commanded by EEC, a warning will be triggered, the filter bypass light, which illuminates prior to fuel diversion. The reason for this is that even if engine damage will occur because bad fuel is burned, reduced engine power is most definitely better than no engine power. This will largely be a summary portion of the lesson, with only one truly new item being discussed here. But it's always good to be fully aware of all safety systems on your aircraft. To keep things fresh, though, we'll start with the new information. To date, 2 737 airframes have been destroyed by near-empty center tank fuel explosions. On the 5th of November 1990, a Philippine Airlines 737-300, and on the 3rd of March 2001, a Thai Airways 737-400. Both tragedies, which in total resulted in 9 fatalities, were found to have the same cause: a near-empty center tank, a high ambient air temperature, and center tank fuel pumps left running. The FAA required modifications be made to the 737's fuel system. These were the nitrogen generating system, hereafter referred to as NGS, and the center tank fuel shutoff system discussed earlier. NGS is a system which removes oxygen, one of the 3 components for combustion, and replaces it with inert nitrogen. The National Transportation Safety Board suggests that an oxygen content of less than 12% is necessary to counter the problem, that is down from the 21% in regular air. The system, developed by Honeywell, is capable of this, pumping nitrogen-enriched air, or NEA, into the tank and pumping oxygen-enriched air, OEA, overboard. Although it is accepted that this is the safest measure, it's extremely expensive and could potentially be impractical. Despite this, 737s produced after August 2006 have had provisions for the system integrated, and all new Boeing 787 aircraft are fitted with it. The automatic center tank pump shutoff was fitted to aircraft made after May 2004. This was covered in more detail in the fuel pump section of this lesson. The fuel vent system is another safety feature of the aircraft. It maintains fuel tank pressure near to that of the ambient air to prevent structural damage to the wing. Vent channels in each tank equalize pressure between tanks and surge tanks when the aircraft is in a climb attitude. Another valve, called the vent float valve, is present specifically to equalize pressure between main tanks number 1 and 2. The vent scoop assembly is also fitted with flame arresters to prevent excessive heat reaching the fuel vent system. Should one become clogged, though, the system is designed so that the pressure relief valve in the surge tanks will open as an alternate source of pressure relief. The final safety measure present in the fuel system is the fuel shutoff valve battery, which was discussed earlier in the valve section of this lesson. The 737, by comparison to many other commercial aircraft, has a fairly simple fuel system. However, as an entity of its own, it's fairly complex. The system has 3 storage tanks and 2 auxiliary surge tanks as a safety feature. Other safety features include the NGS, the center tank pump automatic shutoff, the fuel vent system, and the fuel shutoff valve battery. The fuel system has 6 electrical pumps, plus 4 more in the engine fuel system, discussed further in the engine lesson. It has 5 main valves controlled by the aircrew: the crossfeed valves, the left and right fuel spar valves, and the left and right engine fuel shutoff valves. Standard operations allow it to contain 2 types of fuel, Jet A and Jet A1. Both temperature and quantity parameters are measured by the aircraft and displayed to the flight crew. This lesson covered the following topics: an overview of the fuel system and its configuration, fuel parameter indicators, fuel types used in the system, fuel pumps and their power sources, fuel valves and their power sources, and the integrated safety measures and redundancy. Until next time, throttle on!